Oh, so yeah, yeah, and yeah, and so the idea, the idea of the whole class is actually give you some intuition behind the mathematics that has been used in this domain, and therefore I will of course be writing quite a bit of expressions, but I also would like to give you, maybe if you will, some sort of like, I don't know, engineering mathematics philosophy that which you understand, so that which allows you to understand the relatively relatively complex concepts without like knowing quite a bit of mathematics. Okay, so and that will be based on very simple constructions that are actually used throughout the mathematics, and it comes in different disguises. And the first of them is the projection operation. Okay, so those of you who started linear algebra, you probably know what the projection operation is, and you know that it's based on the notion of the scalar product, right? The scalar product between the two vectors, right? So it's consider two abstract vectors, vector A and vector B, right? And let us just just draw them, assumes them to be two-dimensional, but it holds for any dimensions apparently, what I'm going to tell you. So consider that this is vector A and this is vector B. Okay, we denote the vectors with underscores, and vector A makes angle alpha with x-axis. Okay, and or maybe you want to call it x1 and x2, it doesn't matter. So and angle B makes angle beta is x-axis, and what we will be mostly interested in is this angle gamma that is created by vectors B and A, right? So gamma is an angle that is created by vector B and vector A. Okay, so now the scalar product of two vectors is like fundamental mathematical concept that lies and allows to formulate the notion of spaces, of formal mathematical spaces, because it lies in the foundation of the defining the norm of a vector, right? And so let us, in order to derive it, let us try to think about this vector, this angle gamma, and let's try to make some expressions which will tell us what this actual vector gamma, angle gamma is, or more precisely, what the cosine of this gamma, given the coordinates of the vectors, right? Given that coordinate vector of vector A1 is A1 and A2, right? Transpose, and of vector B, the coordinates is B1 and B2. The reason I put transpose here, because as I already mentioned to you, all vectors, unless like specifically stated, all vectors that we will be dealing with are originally column vectors. Okay, so therefore I'm writing them in a row. Then I need to transform it, transpose it, so that it's a column vector. Okay, so now what you can write, you can write the expressions. For instance, let's write the expression for the sine of alpha first. Okay, so sine of alpha will be it will be basically equal to the second coordinate of vector A, right, which is A2, divided by the absolute value of the length of vector A, right? Because the hypotenuse is the length of vector A, right? This guy, and this is the first coordinate. The sine of the angle is this guy divided by this guy, right? Well, similarly, we can write expression for the cosine of alpha, and in this case, it will be A1 divided by the length of vector A, right? And then we can write the expression for sine of beta, which will analogously will be B divided by the length, B2 divided by the length of B, and cosine of beta is equal B1 divided by the length of B, right? And now we are interested in cosine of gamma. Okay, so according to the expression, trigonometric expression, which you probably all know, it's because it's cosine beta minus alpha, right? Gamma is beta minus alpha, right? So it's cosine of gamma is equal to cosine of beta minus alpha. We have cosine of alpha multiplied by cosine of beta plus sine of alpha multiplied by sine of beta. Okay, this is just a simple trigonometric equation that you probably know from school, even from school. So you can substitute these guys into like, for instance, here, right? This guy, sorry, this guy here, right? And etc. Right? And so you can arrive at the following, like, let's do it basically. So it's let's start from cosines. Okay, so it's a1 divided by the absolute value of a, right? Cosine alpha multiplied by cosine of b, right? So it's b1 divided by the absolute value of a, right? So if I didn't make a mistake, right? So it's let me take a look. I have a note here. So it's yeah, so it's b1 by the absolute value of b, right? So it's cosine of alpha multiplied by cosine of beta. So this guy multiplied by this, right? Plus sines multiplied, which will be a2 multiplied by b2 divided again by the absolute value of a by the absolute value of b, right? So because length of a and length of b, right? Because these guys are the same, right, on the denominator, then we can simply write a1 b1 a2 b2 and then divided by the absolute value of a and absolute value of b, right? So that what's on the top here. So and this is equal to cosine of gamma, right? Because this is what we were originally after, right? So what the thing on the top here is something which is called scalar product of two vectors. Okay, scalar product of two vectors. Okay, of a and b. It's usually denoted as a big dot b. Okay, or it can be also denoted as a transpose b, right? Because it's an operational definition, because a transpose b is, in fact, if you look what a transpose b is, it's a1 a2, right? And the transpose a multiplied by vector b, b1 b2, it will give you, when you multiply vectors, you know how to multiply them, right? You multiply row by the column, and so you get the same expression. You get a1 b1 plus a2 b2, right? So and also sometimes people denote this as a b and they put brackets like this, right? But we will mainly not use this notation. We will either use a times b, like, which is a scalar product, or we use it this way. What's important, this thing is called scalar product, right? So it means that the output is a scalar, it's just a number, and this number is cosine of gamma. And this cosine of gamma is measuring basically a similarity of the directions in which the two vectors are pointing. Okay, so if you look at this picture now, if gamma is 0, meaning that the two vectors are pointing in the same direction, then the scalar, then cosine, then if you take the normalized versions of vector b and of vector a, right? So if you take instead of vector a, you take vector a prime, for instance, which will be vector a divided by the length of vector a, okay? And you take vector b prime, where you will have vector b divided by the length of vector b, right? Then the scalar product of such normalized vectors, like in this case, the norm of vector a prime is equal 1, right? And the norm of vector b prime is also equal 1, right? Then therefore the denominator of this whole thing becomes 1, and therefore scalar product of the two vectors a prime transpose times b prime will be equal by itself, without the normalization, will be equal to the cosine of gamma. Okay, so and this cosine of gamma is basically in a product, in this case, or scalar product, in other words, gives you the access to similarity of these two vectors, because similarity of vectors lies, if we ignore the amplitude of these vectors, so it lies in the similarity of the directions these two vectors are pointing at. Okay, So, and you actually have already encountered this in your, most likely you had already classes, or you've heard when you compute, for instance, the correlation coefficient. Okay, when you compute the correlation coefficient between between some two sequences, for instance, right? If you say, let's say one sequence, you have sequence x1, x2, xn, okay, and let it be also transposed, right, for the strictness. And then you have another sequence, y1, y2. It can be anything, any sequence, right? And then assume for now that the mean of x, basically, which is equal to 1 over n sum of x sub I, is equal to 0, and the same as mean of y, which is equal to 1 over n sum of y sub I, is also equal to 0. You know, this is just for to avoid some unnecessary complications. Then the correlation coefficients of two vectors is basically x transpose y divided by the norm of x divided by the norm of y. Well, this is very simple to show, because you know all the expression for the correlation coefficient. You have to multiply each pairs and sum them up, right? So that will be xi yi divided by sorry, let me get rid of, divided by xi, right, square root, divided by again summation yi, right, which is you could have put squared here, but I just emphasized that. So this is the norm of vector x, this is the norm of vector y, and this is the scalar product of the two vectors, okay? So if you had your vectors normalized, then the correlation coefficient between the two vectors will be basically telling you about the, it will be equal, the correlation coefficient will be equal to simply the scalar product of two vectors, right? And so now if you draw, let's say if you try to visualize it, you have time series like this, and then you have another time series, let's say like this, then clearly these two have very high. Oh, there is something with the network. Yeah.
It seems that in one of your accounts, in one of your we have two Alexes, and in one of
yes,
them,
no, you have two Alexes
yeah.
because but it's all muted. It used to be at least muted.
No, it's not muted now because we're hearing this echo.
It shows no sound.
It was another student. She turned off mic, so it's going to be fine.
Okay. Yes. Yeah, I didn't even connect the audio from the pad, because I have a lecture on the laptop and I have a pad where I'm writing now. Okay. So in this case, if you have these two sequences, right? So let's say this may be a sequence S of t, and well, I mean not S of t, just some signal, and this is sequence S x, which is x of t, which you then when you sampled at certain time instances, right? You from this receive the sequence x1, x2, and etc. Right? And the same for this guy. I'm sorry, the same for this guy. We also had some y of t originally, but you sampled it, and you have y1, y2, and yn, right? And then in this case, you can just simply computing if you normalize them, right? Then by computing the scalar product between the two vectors, you can compute the measure of similarity, right? But this is only one good thing about this scalar product, but another good thing is it actually allows you to compute what I will call the projection, okay? And what we will call through the entire lecture is a projection, okay? The projection is really a fundamental operation. Like if you have a vector A, and let's say you have vector B, and projection of vector A onto vector B is made very simply. You just put the perpendicular to this angle, to this other vector, right? And then the length of this projection, right? This is the length of this, and this is actually the vector itself, right? So it's created how? Very simply, right? You take the absolute value of A, right? The length of A, you multiply it by cosine of the angle between the two vectors, right? Cosine of gamma in this case, right? Multiplied by cosine of gamma, let's call it this way, right? And then this scalar then you need to, because the projection itself is a vector, okay? So therefore now you need to add the direction to this vector, right? How you add the direction to this vector? You multiply this quantity, which will be now the length of our new vector, which is a projection vector. You multiply it by the unit vector that is pointing in the direction of vector B, right? And so how you create this? Well, you create it very simply. You create it by this kind of operation, right? You just simply normalize B by the normal B, right? And then if you rearrange this, and you get model absolute value of A, absolute value of B, and then here you have your cosine, right? Which is basically A transpose B, right? Divided by the absolute value of A by the absolute value of B, right? So this is your this is your cosine, right? And then you multiply it by, so hold on, this is A divided by B. We already took this into account. Now this is a cosine, and yes, and you need to multiply it by vector B, right? So basically you can cross these guys out, and you very easily see that this, how you call it, the scalar product is again the key element in computing the projection. Okay, now the projection is, again, if you talk about the vector, it's a vector whose length is proportional to the similarity between vector A in this case and vector B. Okay, so in both cases, the scalar product appears to be a fundamental operation that helps you to measure the similarity of the two vectors. Okay, so what we'll be dealing today with is actually trying to describe the magnetic field and electric field with some very complicated, from the first view, operations called rotor and divergence. But I'll try to show you that basically all these guys are doing, this rotor and divergence, they're making measurements of vector pattern, of the vector field patterns, or the patterns that vector field forms. They make this, they're trying to make the similarity, measure of similarity between some predefined patterns, like characteristic to rotor and divergence, right? Of the, of the shape of, if you will, of the vector field. Okay, so and this projection operation will be basically used very explicitly, but it will come in a different disguise. But conceptually, this projection operation is what lies in the heart of like a lot of different methods. Like, for instance, you probably all know Fourier transforms, right? You know that if you have a signal, and if you have in the signal certain harmonics, right, and you want to measure the presence of these harmonics in your signal, then all you have to do is you have to compute this. Not everybody understand this, right? This kind of a transform, right? You have to take the integral of your signal with some ej omega t, whatever it is, over dt, right? Things become a little simpler if you talk about the signal that is represented on the discrete grid of samples. Okay, so you sample your data in time, and you create like a set of values here, right? So that it's now it's your data vector, and then this guy gets replaced with sum of s t sub I, right? Values of s at the ith element moment of time, multiplied by this minus j omega t sub I, right? So this horrible dt goes away, and then we just simply have again, if you will, the scalar product of two vectors, the scalar product of vector s t sub I of your samples, what you already seen it here, right? So this is here, and the values of your basis functions, which are complex exponents, but these are just cosine of omega t sub I plus complex square root of -1 multiplied by sine of omega t sub I, right? So these are just two basic, you can think of them as two different basis functions, so you can think about this complex basis function. But again, it's a measure of similarity of your s of t, of this guy, with different harmonics, basically, and your harmonics are indexed by this omega, right? For the very slow omega, you will have something like this, right? For low values of omega. For faster omegas, you will have something like this, right? For higher frequency. And then for some frequency, you have something like this, which will be exactly or very similar to your signal that you are interested in, right? And then if you draw the amount of similarity, you can draw it, and you can express it what is called Fourier spectra, and then you can draw it and say that for this frequency it's low, 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 and this is omega here, right? And for this frequency it's high, and for this again low, 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 low. And this basically shows you that one basis vector, like in this case it will be g omega some k, some specific k t, this basis vector, its cosine, for instance, or its sine, behaves similarly to the signal of interest. Okay, again, this guy is a scalar product, right? And if you go into the space of functions, those are vectors, right? Because we discretize them, and now we work with them like just a set of numbers, basically. But this guy is a function, like these two functions, and this integral of one function weighted by the other function, basically, over some time interval, let's say from 0 to t, right, from some period. This is called also scalar product, but it's a scalar product of two functions. Okay, here we have scalar products of vectors, and you will see this kind of constructions almost everywhere. Every transform, like wavelet transform, Gabor transform, cosine transform, whatever, Fourier transform, almost every transform is based on basically measuring the similarity between something and your data. Okay, and this something is what you choose, which reflects the nature of your signal, right? We are in brain imaging, we are interested in some oscillatory components, some narrow band frequency processes, narrow frequency bands processes. Therefore, we are explicitly, yes, we're using Fourier basis, right? Which has the basis vectors that are focused in frequency domain, okay, in some frequency range, right? Like one frequency corresponds, let's say, to 10 hertz, another one to 12 hertz, yet another one to 14 hertz, and etc. Right? But that just, I'm not going to be talking about Fourier transform today. I just gave you, this is just to give you an example of why this whole thing is important. Okay, and also, by looking at this picture, at this one, okay, you can see that by measuring similarities with different basis vectors, right, which will in this case will be different complex exponents corresponding to different values of omega, you are able to say which component is mainly present in your signal of interest, okay, of what your signal behaves mainly like. Okay, so you basically, of course, it can happen that there is no preference, that your signal, like if you have white noise data, then you don't have any kind of preferences, and it's very difficult to say what your signal actually looks like from the point of view of this harmonic, for instance, set of basis functions, right? But in general, when you do this kind of transform, you're able to say that, well, yeah, that looks more like alpha rhythm, for instance, right? Or this one looks more like beta rhythm, etc. So that also allows you not only to measure the similarity, but also to measure the comparative similarity, how it maps onto different basis functions, onto different shapes, if you will. Okay, and these basis functions do not have to be at all like harmonics or whatever. They have to adhere to certain rules, of course, to certain properties, to be so that we are comfortable working with them. But I mean, it can be actually any shape you are interested in. Okay, all right. So that will be intro to the projections. Okay, because we will use projections today. We will see them. Okay, so that you feel comfortable, right? So for instance, if you have let's say again, if you have, well, yeah, I already said this. Yeah. So basically, you construct A times n, for instance, right? A transpose times n. This is the length of the projection of vector A on n, right? And if you write this guy, then it's not only the length of this projection, but it also the vector that points in the direction of n, but has the length of A transpose n, right? And corresponds to projection of A onto vector n, right? Okay, so now that's a little bit of lyrics, right? So now another little bit of lyrics is because we will be talking about differential equations today in partial derivatives, and we'll talk specifically about the Maxwell equations, and they are originally formulated in a differential form. Okay, so now I want to give you some idea of why we are actually looking at equations in a differential form, right? While let's say all grown-up researchers who are dealing with math and with some continuous signals, they all talk about differential equations, right? Because differential equation is something that describes for you the basic rules that hold on a very little scale, okay? And of course, this very little scale depends on the phenomenon that you're studying, right? If you study, for instance, some chemistry, right, or something, then your very little scale may be limited to molecules, right? If you are going into physics, for instance, into the physics of atoms, right, then your very little scale may be actually the atom, right? Or it can be, the particles that comprise the atom, right? Or if the nucleus, right, the particles that comprise the nucleus, right? The reason for this kind of reduction is because when you are in a relatively micro scale with respect to your phenomenon that you're studying, the rules are very simple. And then the complexity comes from the interaction of different objects that behave very simply according to very simple rules, but when they start interacting, they create the entities which are complex, okay? Therefore, in order to study the phenomenons, you have to go into microscale, okay? Microscale with respect to what you're interested in, okay? So, and therefore, here comes this differential calculus idea. Like at school, when you, let's say, differential calculus, just very briefly, differential calculus, okay? So the idea is very simple. Like at school, when you are asked to compute the distance that body traveling at velocity v passes in some interval t, right? Let's make it t capital, right? Then you just simply multiply v by t, right? And you don't even have a second thought, come on, yeah. Then when you grow up a little bit, they tell you, well, what happens if the body is actually traveling according to some more complex rule? And let's say v of t is some function of time. Let's say it's at, for instance, okay? Then you learn without much of understanding, then you learn, and then in this case, the distance will be at squared divided by 2, right? In this case, it will be the s of t over the time of t seconds if the body started from 0, right? But then when you grow up a little more, they start telling you about why this is actually happening, right? And usually, like in good places, they start telling you by referring back to your early school days and telling you that remember when you were a kid, you had this problem where you were required s v of t, and in this case, if you draw v as a function of time, you get, in this case, you get a straight horizontal line corresponding to the constant value of v, and you were traveling, the body was traveling, was moving at this speed for t seconds, and then your answer was v times t, okay? A smart student would tell you, oh, yes, okay, I understand that v of t is basically the area of this rectangle, right? And then they ask you, okay, what if I travel at this kind of speed? Okay, this is my speed profile, v of t. This is my speed profile, and I traveled for time t seconds. What will be my speed? And then you say that, well, okay, this is just the area under this curve. And you will be absolutely right. And then you are asked, okay, how do I compute this? Okay. And see, it's impossible basically to without going into so-called differential calculus to compute the actual distance traveled by this body that followed this arbitrary profile of speed, right? Why? Well, because you need to somehow estimate this area. And to estimate this area, you all know, right? You split it into little segments, right? And in these little segments, you may think that your speed is constant, right? And then you can split it in segments. Then in each segment, you have v times delta t is your delta s, right? And then usually when you are dealing with some smooth signals, right, you say that, okay, well, I'm interested in how it happens in a very, very small moment of time. You're saying that, okay, let's make delta t go to 0, and you denote this by replacing delta t with dt, which is and s with ds, because accordingly your s will be very small for very small d, right? So it will be ds equal v times dt. Okay, so this is one way of, and to be correct, I have to put t here, right? V of t, right? Because it's v of t, it's a profile of my v with how it changes with time, right? So I put t here as well, right? Okay, so let me delete this and and write the new one, v of t times d of t. Okay, so or you can write it this way. You can say that the increment, the change of s with respect to during the interval dt, will be proportional to the actual speed, right? To the actual, to the velocity, and and so then you can make things however complex you want, because then you can say that, okay, my v of t is certain profile, but it also depends maybe on some, and that also ds of t, right? And then it depends on some other function, right? And then you can say that, well, actual dv dt is the change in speed is proportional to some other function, which in this case will be the acceleration, clearly, right? And then you can make this things as complicated as possible, by increasing this number of equations, and also you can add the directions. You can say that, for instance, well, your body can travel, let's say, in 2 dimensions, right? And so you may have vx, for instance, profile of t, and you may have vy of t. Okay, so two vectors, and then you can write different equations about each of these vector, and the total vector, the total displacement, will be pointing in this direction in this case, right? And then you can play with this, right? So, but however however complicated it will turn out, it all started from a very, very simple rule, because on this micro scale, this whole thing is very simple, right? It's like this, right? Then let's try somehow bring this together, right? So now assume that vector v is v of t is your vx of t and vy of t, okay? So it has 2 elements, right? And assume, yes, indeed, you have this expression. You have the expression. You can have a vector equation in this case, right? You can say that d vector s of t increment in type dt, right? Its change is proportional to v of t, where v of t is your vector. It's vx of t and vy of t, right? Okay, so we are just kind of approaching from very, very far away, the idea of describing the fields. Okay, so but so that something you can really understand with this, speeds and velocities, and displacements. It's something you can really feel. Therefore, I decided to do it this way. Okay, so now assume that you have let's say your body starts moving from this point, and let's say you are interested in this body reaching this guy. Okay, this will be in blue. This will be your target. Okay, this will be your blue sky. Okay, so, and then, but the body is actually traveling in a certain way, like very complicated way, and finally arrives at this point, right? You can basically create a straight line, right? You can make a straight line here, and you can call, if you are interested in, right? You can be interested in evaluating how well the trajectory of your body actually adheres to the let's say this will be y of t, right? And this will be x of t, right? How it's changing. So how well the trajectory of your body adheres to the general direction that you are expecting this body to move, or the most optimal direction, right? Because this line represents the shortest path, right? So then you can specify certain vector, right? And it can be a unit vector, and let's call it this way, a vector a. Okay, and let us just simply call the movement in this direction, let's just call it, okay? We call the reason why I named the vector a is because a comes from word aspiration, okay? Aspiration, or from word aspire, if you will, right? So and the amount of movement in this direction we will call aspiration, and the amount of movement in amount of movement in this direction we will call deviation. Okay, right? So how do you measure this amount? How do you actually at least see at each time moment how much the body is aspiring and how much this body is deviating? Well, it is actually very simple, right? You can simply take d, vector d, which is not, it's not no coincidence, this d is separate from this d, okay? So this d and this d, they're not, that they have nothing to do together. It's just because it's deviation, okay? Okay, or maybe, let's better call it not d, call it e, okay? Vector e, like error, okay? But we still talk about it as deviation, okay? Then aspiration, the amount of aspiration, if you will, can be equal to A transpose multiple. You can define it, right? By like A transpose multiplied by vector V. Because it will be a projection, like in this case, for example, in this case, your vector V is in this direction, and it's exactly parallel to this guy. So all your speed, all your vector, all your movement will be in direction of aspiration, and that's good in this case, right? But for instance, at this time moment, your vector is very much perpendicular to your aspiration, right? And it will be more erroneous vector, right? It will be described by e direction by your deviation, right? So therefore, at this point of time, or at each point of time, and because the location in the xy plane is parameterized with time, then at each point of time, or in some specific locations along the trajectory, you can quantify the amount with which your particle is moving to your blue sky location, or the amount which is deviating from this blue sky location. Okay, now imagine if you have many such particles, okay, and let's say this is yet another particle, this is another particle, another, there are many of them, okay, and at each time moment you can create vectors of speeds, for each of such particle, okay, and then clearly you start getting very, very complicated picture, which already will be very difficult to describe as just a single aspiration or a single vector. You need to create something more elaborate. But conceptually, you again will be creating those things, and yes, we will be doing them in a differential scale. Yes, and they will be not trivial to understand why this thing means what it means, and I'll show you what it means actually, and explain why this means a certain thing. But in the long run, in the end, it will all be just a projection of very specific pattern of your data onto some very specific pattern. Okay, so with this, I think we need to switch to the. Let me see if there is something else I wanted to convey to you along these lines, but maybe not. Yeah, so that was aspiration, deviation. Yeah. Okay. So yes, one more thing. So there are basically three kind of related but unrelated stories. The first one about the scalar product, this one about differential calculus, and then I connected this thing to to assessing the pattern of movements, and so I basically use the scalar product here, right, to show how you can measure the amount of the desired behavior of your particle in this case, right, or specific behavior doesn't have to be desired. And there is one last thing, very simple again, and it's all linked to the differential calculus, but very simple. Okay, so if you have a base, oops, sorry, there's something wrong.
I'm sorry. When you're showing this guy, your pointer is прозрачный.
Yes, transparent. Yes, I know that, and I tried to fight this, and I couldn't find a way to fight it. I'm very sorry. That's why I'm trying to somehow to circle it, and
okay, that's okay. It's just hard to find, and when you finish showing, I just realized what were you showing.
That's unfortunately,
okay if you can't.
Yeah, that's unfortunately the problem. I will try to fight it, but I even asked OpenAI chatbot today how to change the pointer, the shape of the what the pointer is showing, but I mean, yeah, I'm sorry, I couldn't. Yeah.
That's okay.
But I will
Thank you.
because for the second part of the lecture it will be the slides, okay, that I have prepared, and so I will have normal mouse pointer, okay, so I will be pointing to the
Okay.
and yeah, sorry, bear with me a little bit, and please do interrupt me if something gets not clear. You don't see the pointer of the mouse because yes, it is transparent, and this is horrible. I actually hate this Galaxy tab. It's horrible. Okay, anyway, so let's talk about a little bit more, right? But so we will use this, and that's why I'm telling you. You had this preparatory class on mathematics, and like there is a very simple thing, very simple concept. If you have some function f of t, okay, I'm sorry, not f of t somehow. Let's say you have a function f of t, okay, and then let's look at this value of the function at some time instance t0, okay, and let's say you are interested in the value of this function at another moment, which is very close to the moment t0, you know. Let's say it outstands from t0 by this very small amount dt, right? Then you should know this, right? You should know that basically the derivative of the function, this function is the function of one variable only, and the derivative of the function basically corresponds to this angle, right? Which, you know, which this tangential line and the horizontal axis make with each other, right? So therefore, it's very natural to be able to predict the value of this function using the derivative of the function multiplied by this dt. So basically, f of t plus the dt is equal is t0 is equal f of t0 plus df dt, which is the value of the derivative at location t0 multiplied by dt. Okay, so it's simply a linear approximation of the function. Okay, so it's basically a trivial thing, and this is it's basically the first two members of so-called Taylor series expansions, right? Which you should be aware of. Taylor series expansion, and we will be using this in the subsequent slides so that you're aware of this. Okay, so it's just simply a linear continuation of your function by a very short interval, right? And so you approximate that it's linear, and what is the speed of growth of this function? Well, it's equal to the derivative at point t0, and then you can forecast what will be the value of this function next, right? So if the derivative is positive, then it will be growing. Definitely, if the derivative is negative, it will be descending. The function will be descending. So yeah, so this is something that you remember and you understand when I refer to it in the slides. Okay, so yeah, I think that's it, and we can go to differential vector calculus. Okay, so the operations that we will need today when we talk about Maxwell equations. Okay, so all right, let me try to stop sharing this. Let me start share screen here. Okay, all right, now those are just this lecture now that I put. Yeah, but anyway, here let's start. You can see my screen, right? Hello?
Yes.
Yes, cool. And now the pointer is good, right? So you can see the mouse well.
Yes.
Yeah, okay, a little chaotic, but yeah. All right. So now we need when you talk about just a scalar function, right? Then it's very simple. You describe it with gradient with derivatives, right? And it's all scalar and there's no problem, right? But here we wanted to describe the moving of the particle even in a two-dimensional space, and we had to go already into vectors. Okay. Now consider a function of two variables, in this case y and x. Okay, and let's say this function looks like this. Okay, just it may be a Gaussian, doesn't matter actually, some sort of a function, basically a surface that is defined over the two-dimensional space, right? So you can basically take each element, each value of x and y, and you can compute the quantities, and then you will always appear somewhere on this surface, right? There is such thing like gradient, which is very close to the notion of derivative. Okay, very close to the notion of derivative. And sorry, I'll do this just a second. I'll need to connect this piece of crap to the electricity because it's dying. Okay, so yeah, so but now because you have already 2 dimensions, right? The gradient or your derivative, if you will, is now a vector that is pointing, in this case, somewhere in 2 dimensions, right? Somewhere, and shows you the increase of this function, right? Like in this case, right? So if you now look at this function from the top, and the darker the higher, okay? So then you look at it from the top, then basically at each point you compute the gradient, then the gradient will be a vector that is pointing towards the ascent direction at this point, right? So if you now well, what is the gradient? Okay, well, first how you can compute it. Well, you can understand this probably from this plot on the right. So on the right, I show you a different function that in 3D will look probably something like this, and it will be growing as you move from large values of x to small values of x, right? In this direction. And so that the gradient is clearly, and it's not changing along other direction, okay, along z direction, right? And then basically the gradient clearly is a vector that will be pointing in the just along x-axis, right? But in the negative direction with respect to x-axis, right? And it will be 0 with respect to y-axis, right? Therefore, here is an idea. Why don't we compute the direction of ascent by measuring the extent to which the function changes along x direction, like here, and assign and say and this is basically like a projection, if you will, but it's not really a projection. But anyway, this is some quantity which tells you the change of function with change of function u with respect to x, and because orthonormal vector I is pointing along x direction, this is the convention, right? Then you say that, okay, this is my component of my gradient vector pointing along x, right? Then you do the same thing. You measure the ascent, the change of your function with respect to y direction, and you multiply it by the ort j, and then you do the same thing with respect to z if you have function of 3 dimensions, right? Of 3 variables. In this case, we have function of only 2 variables, and therefore our gradient will be just this guy. So let me try this with this, although this is a piece of crap, but yeah, this will be in our case in 2 dimensions. Our gradient will be given by these 2 elements, right? Okay, so you have to note also that taking the gradient of the scalar function, so this function is a scalar, right? It's just a number for different values of x and y. It's just a single number, so it's a scalar function. Yes, it's a function of several variables, but this is a scalar function itself, right? Because it outputs a scalar, a single number for each value of x, y, and z. Okay, so the gradient of this function nevertheless gives you a vector field, right? Because it's a set of vectors. At each location, you can compute this vector. It's really continuous and nice looking field because the function is smooth and nice looking. So and yeah, so it's a vector field. Okay, so this is just your first example of vector field. Well, the second one, after this set of velocities of different particles that move and aspire towards the blue sky. Okay, so now in order to, there is a lot of interesting relations in maths, and some of them are actually derived just based on some formalities, basically on a formal similarities. And here is one example. So to denote the derivative and the gradient, to denote the gradient, we will use an operator called nabla. And it's an operator, but it's a vector, okay? So it's a vector whose elements are formally d dx, d dy, and d dz, right? So, and then your gradient is your vector nabla, it's called nabla, or sometimes it's called del, transpose, right? And multiplied, sorry, this is my mistake. No, of course, not multiplied, no, not this way, not transpose. It's a vector, because it's a vector, it's basically d dx, and d dy, right? And then you need to scale it with your function, because your function is a scalar, right? In this case, of 2 variables only, right? And then basically you get, because it's a vector, this is just a scalar. It means that this scalar applies to each of the element of this vector, right? So basically d uxy dx, d uxy dy, and therefore you can write the gradient of your function as simply nabla times u. And you have to remember that this multiplication, it's not a scalar multiplication, you know, it's not multiplication of two vectors, it's scaling of vector nabla by function u. Okay, I think more appropriately or more conventionally, it will be to write something like this, u times nabla, but you know, it doesn't work this way usually, but usually they say nabla u. Okay, so this is the gradient. Okay, so the importance of gradients, that's actually I'm taking quite a bit of plots today from the materials that I gave you to read before the lecture, and I hope you did so, because it really will simplify your understanding. So again, if you take the function and these different colored lines correspond to the level lines of the function. Okay, this is the largest values, the function reaches its largest values within these spots, right? Then it's in this level it's smaller, in this level it's even smaller, and etc. Okay, so then if you compute at this point, if you compute the gradient of this function, first of all, the gradient will be orthogonal to the level line. Okay, it will be orthogonal to the tangential line, to the tangential line with respect to a level line, but it doesn't really matter that much for now. But if you want to compute the speed of ascent of your function, or not speed, but actually the amount of movement of your function, the derivative of your function with respect to some specific direction given by vector dr, right? Then you have to project the vector of gradient on vector dr. Okay, so just simply project vector gradient and this guy on vector dr. You already know the direction you are interested in, but the speed of change of the function along the direction will be equal to the value of the length of this projection. So it's basically a scalar product of gradient with vector dr as long as vector dr is normalized. Okay, so then that just another application of projection, which of the scalar product that is, I think now should be trivial to you, but it's kind of obvious, right? So you basically take the scalar product of your gradient vector and your vector dr, and then see how it changes with respect to s, where s is displacement along vector dr. Okay, so anyway, let's go next. If you have questions, please do ask. Okay, so this function that I've showed to the gradient, so it looks like it's something that gives rise to the vector field. Okay, we'll come back to this guy, and the reason I called it u, and the reason the authors of that document called it u, is not just random reason. It's just because u in electric field is called a potential function. Okay, and we will arrive today at some result that will show to you what actually the potential of electric field, and this, you all heard like difference of potentials, right, or the voltage, right? We will see from the very bottom what this actual potential is, okay, what this function is, and how the gradient of this function actually gives rise to the electric field. Okay, so but so far just relax. Okay, just relax and assume that you have the field like this, and you need to somehow quantify this field. Okay, now, well, you look at this field and you have some very interesting patterns in here, right? You have some sort of rotations here, for instance, right? You have some sort of like places where everything dies in, right? Like something like a sink, for instance, right? Where all field lines are sinking and dying. Like if you assume that this is your bus stop or a toilet or whatever, and then those are your lines, which are the water. Each line corresponds to the velocity of the water of the little cube of water at this place, and then this is basically where it all like stops, for instance, right? It's the water dwells at some lower niche, right? Or if you can have a different kind of shape, you could have, like, for instance, you can have a field lines looking like this, right? Then it will tell you that the vector field basically at this point it's leaving the game, right? It's leaving it. It's basically, if you talk about the water, you think that this may be some hole where this water is floating to, right? And just leaving the well, right? So the well. So, or you can have, for instance, up this kind of patterns, right? You can have some sort of rotations, right, in your field, right? Rotating patterns, like a whirlpool or something else. And you want to be able to describe these two phenomena, because it turns out, according to Helmholtz decomposition, we're not covering it here, but according to Helmholtz decomposition, if you can decompose any smooth field into the elements of the field that are described by this pattern, which we will call divergence, okay? And I will tell you why. And you have to divergence. And you have to make a connection now to this aspiration, right? Because remember this aspiration, we were interested in moving to the blue sky, and we made this vector and we defined aspiration. Here we are interested into this kind of patterns, and we call this pattern divergence, and it can be positive, it can be negative. This one is negative divergence, or else it can be a positive divergence, because if you assume that your vector field, for instance, go in this direction, therefore you have a spring here, and it's influxing the water into your well, right? And therefore it will be the field lines will diverge. Okay, that's why it's called divergence. Okay, and this guy and basically divergence and the rotor are the two main things, or the curl, the two main things that will be used to describe the field, that are used actually to describe the fields in almost every discipline. Those are two main things, because according to as I said already, to Helmholtz decomposition, you can have two. If you know how to decompose your field in these two guys, then you can describe any field. I will later tell you why it's actually so, but very briefly, again graphically, and again we'll refer to the vectors and basis vectors and things like that. But let's assume that now we want to somehow find how we can compute the divergence of the field. Basically, how we can, by going through basically each point over the space where the field is defined, how we can compute some quantity, which we will call divergence, and the high value of this will tell us that this kind of pattern is present and is very intense, and low or negative value of this will basically tell us about the presence of some source at this location, right? Of some influx of field lines into your plate, right? Or into your field of into your plane, right, where you're studying, since or where it's negative, where it tells you that it will be efflux, like outflux, right, of your vectors, right? So let's see how we can do it. Okay, so to do it will be maybe a little bit complicated, but don't be afraid. Just you can interrupt me and ask. Okay, now as I already mentioned here, I assume that you're taking this little square in your plane where you're studying, or maybe even 3D, right? But I've drawn here only a plane. In your volume, but you're studying your vector field. Okay, and assume that you then this volume, right? And now, well, think about this way. If there is, and this line is your vector line, vector field line, and there are many of them, right? But because it's a very small segment of space, they are all the same. They're all like parallel to this guy, right? So assume that if there are no sources and no sinks inside this little volume, then the amount of water that flows in and the amount of water that flows out, and it can flow in all different directions, of course, but the amount of water that comes in through all possible directions and the amount of water that leaves this volume is the same, right? And if it's not the same, then it means there is something happening in this volume, right? It means that there is something changing there. It means that there is some source or sink in that volume, right? Okay, so let's try and just simply quantify the amount of water passing in. Assume that vector A is a vector whose length is proportional to the speed at which water is flowing through some finite area, through some unit area, right? Then in order to multiply how much of water has flown in, you have to multiply the speed, this value, or the length of A, by the elementary elementary area, right, which you're studying now. Okay, and again, we are in differential calculus, so our area is denoted, our dimensions here are x, y, and z, and the displacement along each of them is defined by dy, dx, and dz, right? Okay, there is one other thing for you that very useful. The normal vectors, okay, this vector ds, it's called s because we are talking about area, right? Its length of this vector is proportional to the area of this page. Okay, it's dx multiplied by dz, right? And the vector itself is perpendicular to this guy, okay, to this plane, right? So why? Because we need this in order to measure the amount of water that are actually floating in through this phase, right? Because imagine if the vector is pointing parallel to this phase, then you can compute the direction of this vector with and scalar product again of the vector with this normal vector, and you get 0. It means that through this phase, no vector field is coming into this volume, right? But if the angle is, if the cosine of angle is not 0, then some of the flow is coming inside, right? So all right. So now let's see how much of water is coming in through this phase. So it's basically because the water is coming in, right? So we have but the phase normal is negative with respect to field direction. Then we will have minus ay, which is the component of a along y direction at this point, x, y, z, multiplied by dz and dx, right? So this will be the amount of water that's passing through this phase, okay? Passing inside, okay? The amount of water that is passing through this phase, again, taking into account the normal, will be given by this expression. And here we will use the value of the field, not at this point, but at this value of y, right? Which will be at y plus dy, which we will approximate, as I already showed to you, by derivative of ay with respect to y multiplied by dy, right? Remember the Taylor series expansion thing, right? So that means that this the amount of water here through this phase will be equal to ay plus day dy, whatever dx dz, okay? And then you can sum these two, and it's very easy to see that the only guy that survives is this guy, day dy times dy dx dz, right? And then dz dx dz. So, and you can then write this, and dy dx dz is already the element of volume, right? And that's why we denoted dv. So it means that if anything is happening inside irregular with the component of the vector field that is pointing along y direction, it's reflected by this quantity, which is simply the rate at which ay is changing with respect to y direction, right? Multiplied by the size of the small volume, right? Okay, so apparently you can do very similar thing with respect to these two faces and with respect to this and that faces, and you get the same thing, right? And then you just simply say that the amount of inflow is equal, of the difference between the inflow and outflow is equal to this quantity multiplied by dv. So you need to take this quantity and multiply it by dv, and if you want to extrapolate it to the whole volume, then you of course have to sum all these or integrate all this with respect to the volume. But we are in a differential calculus here, so we don't have to integrate anything. We just say that, okay, this is an interesting quantity because it tells us about the difference between the inflow and outflow of our field vector, okay? And therefore and if this guy is positive, it means that there is some actual inflow. If the guy is positive at specific location, at specific x, y, and z coordinate, then there is inflow, there is a source at this location. Or if it's negative, then there is a sink, right? And therefore we call this guy divergence, assuming that when it's positive, it's divergence, and when it's negative divergence, okay? It's convergence, if you will. And then again, operator nabla comes handy, but now we don't scale it, but we take a scalar product of operator nabla and field vector A. Okay, because you need to make the sum. You need to have a scalar because divergence is a scalar, right? And therefore you need to take the vector ddx, ddy, ddz multiplied by the elements of vector A, right? Okay, so and maybe a slightly simpler explanation. Maybe if you, let's say, you can do it this way, right? Well, this is a basic pattern you are looking at, right? Right, something like this, right? Now, if you look in this direction, if you look in this direction, basically this pattern is very characteristic to the fact that the vector was pointing in this direction here, and after this point, the vector is pointing in completely opposite direction. So the derivative, the change of this vector with respect to this axis, let's say this axis y, is large, right? Because it's a single point, it's changing the direction by the opposite. And if you take the limit, you will get large value here, right? Well, the same, you can do the same thing along x-axis and along z-axis, and that will be exactly what this divergence is. Okay, it's just not clear if you do it the way I just explained to you with this simple thing, whether it quantifies the whole inflow, right? Maybe it's just some sort of coincidence and some heuristics, but in fact, this one is this more formal thing. Again, it's not a very formal proof because it doesn't take into account the invariance to the coordinate system, but for this class, I think it's more than enough. Okay, so this is the divergence. Okay. Now, and there, yeah, this was an example for you that it's like a let me clean this. Yeah, so it's if the divergence is positive, that means there is some spring floating at this particular location, and if you try to describe the field of water molecules or water elements, the field of speed of water, small volumes, then it will have a positive divergence at this point. Okay, now. This is another quantity that we are interested in, and it's actually called curl. Okay, and this is the amount with which your field lines are rotating. The example of it is here. You quite often see it when you flush the water in a toilet. It starts rotating, or maybe in a bus stop. It's also, when it's sinking in and it's finished, and you see that there is a whirlpool that happens, and it's rotating, right? So, and if you draw the speed line, the velocity lines here, they will look maybe something like in this plot. Okay, so the curl from the very beginning, it's given by an incomprehensible set of equations or set of expressions. It's basically, but let's first talk about its properties. Okay, how if we want to describe a rotation, right? Let's say forget about like field lines, right? Think about some particle that is rotating, right? Okay, there is a speed of rotation, right? The rate, how many circulations per minute or per second, whatever it makes, right? And there is also a plane in which this particle is rotating, right? So, and the way to define it with a single element is to basically say that we have a vector that is perpendicular to the plane of rotation, because then it's uniquely defined the plane, right? And then its length of this vector is proportional to the rate of rotation, to how fast it's rotating. Okay, so you basically can say that this is the and this is basically what angular velocity is. Not many of you know, or maybe some of you know, that angular velocity is actually a vector, and the vector that is pointing in the direction perpendicular to the plane of rotation. Okay, if you studied gyroscopes, and without this kind of notion, it's impossible to explain why gyroscope is working. Okay, so anyway, yeah, so the vector is given by this expression, the rotor is given by this expression, or a curl. We sometimes call it rotor, sometimes call it curl, and it's again can be described by the product of the nabla operator with your vector, but now it's a cross product. Okay, it's so-called vector product. You should know what this vector product is, and it is given by the determinant of this kind of a construction, which is not clear at all why it is, and therefore let's try to understand it. Okay. Again, see, when we talked about divergence, we basically developed some procedure with which we matched the desired pattern of the field with the desired pattern, right? We basically computed the similarity. Here again, the same thing. We are trying to measure what's so-called circulation of the field. Okay, so the amount of rotation, but we want it within some unit area, right? So that it's not like the overall circulation, but divided by the area where it's circulating. So it's like amount of circulation per unit area, and that's what our curl is. But the circulation itself is formally given by the contour integral of your vector A at each point along this contour, or the circular contour, projected on vector dr, where dr at each point is a tangential line, which is the line that is tangential to the circle. Okay, so basically you're at this point, you're like in this case, very easy to see. Let's say you draw a circle here, for instance, right? And then you can see that all vectors are very nicely aligned with the tangential at each point, right? Of course, you move to the next point, then this guy is rotated, but it's aligned with another vector, which is tangential to the circle at this location, and it's like here, for instance, right? Like in this, where the vectors are drawn, they're all absolutely coinciding with tangential lines with respect to the circle, right? And therefore, this integral is simply a summation of vector field lines, vector field, these vectors that are comprised in the field, right, projected on these elementary dr vectors, which are the tangential vectors to this contour, to this circular contour, right? And that's what's called that. This is a circulation, and we are interested in the circulation per unit area, right? Let's see. So it's actually not very difficult. Now, again, assume that you have some vector field, and assume that you've taken a small element in space, and assume that you are now looking within some particular plane, and now it's XY plane, and we are trying to assess the rotation in this plane, because technically it can be rotating within some arbitrary plane, but its amount of rotation in this plane is comprises rotations in XY plane, in YZ plane, and in ZX plane, for instance, right? Not for instance, but so therefore we look at single plane, and let's look, because it's a small element, then it doesn't matter if we make it circular or we make it rectangular, but let's make this contour, okay? And those are DRs, basically, our DRs that I've showed to you there, right? So now let's see how much of this circulation we can calculate here. Okay, the trick is exactly the same. Okay, so as before with divergence. So basically ax times dx along this line, along this side, then the field has changed because we are now at coordinate x plus dx, so it will be ay y component here, right? Because only y component contributes to the circulation, because x components is perpendicular to this guy, right? So ay time of at x plus dx multiplied by the displacement along dy by dy, plus in this case minus, because the contour line is pointing in this direction, but the vector field line is pointing in the opposite direction. So it's minus this guy, but evaluated at y plus dy, which is here, and dx clearly, and etc. And the last one, right? A minus ay dy, right? So now you are, as before, we will approximate this guy by its first difference, basically using the first order expansion and Taylor series, by just taking the derivative of ay with respect to x and multiply it by the displacement, my micro displacement along the x-axis, right? And then you get this guy times dy minus this minus that. Now, of course, clearly these guys will disappear, right? And the only thing which is left is day dx minus dax dy multiplied by the area, by this elementary area we worked at, by dx dy, right? If we are interested in circulation with respect to the unit area, then we have to technically divide by dx dy, or just we have to take something which is next to it, right? You don't have to divide, but this if you divide, we'll get this. So this guy, this difference of the two derivatives, is something that quantifies the amount of rotation in xy plane, okay? And this is the guy that is an element of our curl vector that is pointing along k direction, right? Along z direction. And this is vector, this is direction z. It's showing to you that it's looking from the screen onto you. And the length of this element of the curl vector is this one, okay? And the same you can do with with z x plane, and you can do the same with y z plane. And then you get this expression that first you might think that's completely incomprehensible, but now you can see that it's not that unreasonable, right? So basically you can see that this one is the difference of the amount of y component of the vector changes with respect to x minus the amount of x component of the vector changes with respect to y. Because if it's a rotation, it's ideal, it's not changing, it's just rotating, okay? So this one is not changing here, this one is not changing here, right? So, and then you from this, you create this vector, the curl, that is a vector that is pointing in the direction perpendicular to the plane of rotation, right? And the length of this vector is equal to the amount of, to the speed of this rotation, okay? So, and we denote it with nabla A because it's just by this kind of, like by some magic coincidence, it's actually equal to the vector product of operator nabla and the vector field. And again, you have to understand that this value can be computed at each element, at each point in space. So, and the rotor in general, or curl, is like the same as the divergence. In some places, in some locations in space, it can be positive, sometimes it can be negative, somewhere it can be absent. Okay, there are some very special fields where a rotor of the field is always zero. Okay, those are called potential fields, and actually the gravity field is one example. And they have very, very special properties. Okay, then I will talk to you about this because the electric fields that we will be working with the quasi-static approximation are actually potential fields. Okay, so, and again, as I mentioned already, this thing is related to the angular velocity, where angular velocity is a vector perpendicular to the plane of in which a particle is rotating. Okay, so, and see again, the use of this scalar, the use of this vector product allows you to go into the plane orthogonal to the plane where things are happening, right? So basically you have a radius here, you have your linear velocity here, and then by taking the vector product of this guy, and this guy, you by definition of the vector product, you end up in an orthogonal plane, right? You end up in an orthogonal plane, and the only thing that I'm not sure here that the direction with what I've drawn, direction is correct. Yeah, I think it's because it's counterclockwise. Yes, I think that's right. You use this rule from school, right? That rotate, this shows the rotation, and this shows the direction of, this is when you talk about the current, right? It's like a magnetic field and the current, and that's what we are actually after today. Therefore, this whole rotation thing comes very, very handy. Okay. So, all right. So see, we have half an hour to go. I have material for this half an hour till the end of the lecture. Okay. It's a short lecture today, but I want to cover all the material. May I kindly ask to stay with me so we don't make a break. Okay, please.
Maybe like only 2 minutes or something like this. Just,
okay. Go grab some water. Yes.
Yeah. Thank you.
Yeah. Okay, can we start?
Yes, okay.
Okay, cool. Thank you very much. Yeah, I'm sorry. I mean, it really didn't depend on me, today's schedule. I couldn't leave. I would love to, but you know. Anyway, so Maxwell equations, okay? It's well, frankly, it's not that you will be using every day, or I don't know, will have, well, most of you, right? So, but still, I think you need to understand where things are coming from, right? And therefore, I decided to include in this class, and I actually made this year this part much shorter. Therefore, I want to go through this lecture today and finish it, and you know, just so that you not forget, but we covered this, and you kind of understand and see the big picture. But I do not actually require your understanding the details of this, of course, because it's impossible. It's like, in order to understand it, you need to take the course on electrodynamics. I understand this, right? So anyway, so the Maxwell equations, you know, they're formulated this way. So first of all, you have two vector fields, right? You have E and B, and you probably seen this kind of pictures where you have, let's say, electric fields changing this way, and let's say magnetic field in the orthogonal direction. If I have to be correct, it has to be shifted by pi/2, right? I'm not a good drawer at all, so therefore I apologize, but those are supposed to be happening in two different planes, okay? Especially this plan with this, so in two different planes, in orthogonal, mutually orthogonal planes, and you have vector, let's say, B of x, y, and t. This is how it's changing, and this is vector E, x, y, and t. Okay, and this is how it whole thing unfolds in time, right? So you have two vectors perpendicular to each other, and their sizes are connected such that vector B, its change makes E to appear, and then change of vector E makes vector B to appear, okay? And then they, you know, push each other this way, and that's what makes the radio waves propagate so far, right? Like in outer space, whatever, almost without dissipation, right? Especially if you talk about the media where there are no conductive particles, right? So in our case, in the brain, if the brain signals were like this, and if they generated the fields like this, then we ourselves would be, each of us would be a radio, okay? So this is not the case. So the fields that we are dealing with in the brain are actually weak, and the reason they are weak is because they are very slow. They are very slowly changing compared to the conductive properties of our head, okay? And therefore, we are using so-called quasi-static approximations of Maxwell equations, and we will cover them on this slide, but let's first look at the Maxwell equations themselves, okay? So the first Maxwell equation is actually very simple to understand. This is something you already know. This is the scalar product of nabla with vector E at location R, given by a radius vector, right, and at time t. And this is what we call divergence, right? And this divergence is equal to the density of charges at this point R at time moment t. Very natural, right? If you have a charge, you all remember, right? It was positive charge, then you have, you have positive charge, you have these field lines pointing in this direction, right, from this charge, and therefore, basically, you have non-zero divergence here, right? This is clear, right? And this divergence, as it turns out, it's proportional to the density of this charge. Again, we are in differential world. So we are not talking about the charge, but we are talking about the charge per some unit volume, right? To something very small, right? Therefore, therefore I call it a density, you know, charge density, right? We will be talking about current density as well, but the charge density is the amount of charge, electric charge per volume, per element of volume. Okay, that must be clear, right? So there's nothing really difficult here at all. Now, the second one may be a little more complicated, but again, bear. Rotor of vector E is equal to the change of vector B in time. Not only so, there are two things it's telling you. The first thing is that the size, the change, not the change actually, but the vector E itself is proportional to the amount of change in time of vector B. This is induction, right? This is Faraday's induction. Remember, when the B changes, it makes the electric field, electrical force in the contour, right? If you have a contour and if you have a electric field, and if you switch off the field, then the electrodynamic force occurs that is trying to compensate for this field, right? And trying to kind of recreate this, right? Because one thing, maybe you will find it, at least maybe you will remember it. Well, the inertia, right? Inertia is a fundamental thing, right? In this world. Well, the Richard Feynman says that magnetic field is the inertia of the electric field. Okay. So when the electric field tries to change, the magnetic field kicks in, and the other way around. The magnetic field changes, but the electric field compensates. Okay, so and we will see this in both equations here, in this one and in this one. But let's first talking about this one. Now, the second thing it's telling you that the vector E is actually happening in the plane perpendicular to vector B, because B is your, let's say, your speed, right? The velocity, the linear velocity, right? But rotor is something which happens in the perpendicular line, right? Rotor is pointing in the direction perpendicular to the plane of rotation. So therefore, if B is happening in some, and it's rotating, it's happening in this rotation, it's happening in some plane, then it generates E, which is perpendicular to and this change happening along the wire, for instance, which is directed perpendicular to the plane in which vector B lives. Okay, that's what it tells you. Okay, so now divergence of B is equal to 0. Well, knowing this, you can say that this means that there are no magnetic charges. There are no isolated magnetic charges. There is no particles that create magnetic field. That's actually funny, right? We only have pluses and minuses together, but we have magnets, of course, but they have both plus and minus, right? There are no isolated magnetic charges, and therefore the divergence of the magnetic field is always 0, because there are simply no magnetic charges. And that's actually one of the reasons why a magnetic field is not independent. It depends on E, on the electrical field, and electrical field is the primary thing, and then there is magnetic field. Okay, so, and then the next equation tells you again the reciprocal story. It tells you, well, actually changing of electrical current gives rise to vector B, and this vector B is rotating in the plane orthogonal along which this electrical field is pointing and changing, right? So it's basically, you probably all remember this wire, right? So there's a wire and there is a current floating through, and there are the magnetic field due to the wire, due to just the current itself, there will be magnetic field here. And if this current is changing, this magnetic field will also be changing, because it will try to create the magnetic field to compensate for the change of E, to keep it. That's why we have all these transients. That's why we have sometimes our electrical lamps, they get broken, right? Because we have some transient processes which are due to this magnetic field, the parasitic magnetic field that occurs. Okay, trying to counteract, your switching off the switch in your apartment, right? So there are, and yes, it tells you that there are two sources of the magnetic field, basically. The first one is the current itself. If the current is there, then it will generate a magnetic field, right? And the stronger the current, again, here we talk about the current density, okay? So because per volume, per element of volume. But the stronger, the more the denser the current is, the more intense the current is, the faster this field will rotate. So this rotor just tells you that it's rotating in a plane that is perpendicular to the plane to the line along which vector E is pointed. Okay, so that's all. So, and then the second component tells you that yes, the change of E will also create vector B. Okay, will also contribute to the rotor, to the not to the rotor itself, but just to vector B, to the height of this vector B, which is a rotor, right? Okay, now the field itself, or the electrical current itself, actually is comprises two currents, basically two main things. Okay, this one you can largely ignore. I mean, we will not look into it today. I mean, but but this is called displacement current. It's kind of important. It explains how the alternating current, how the alternating current makes it through the capacitor, right? We had this joke at school that, you know, when you have a DC current, when it goes this way, it just hits the wall and stops, right? And you have the AC current, it just jumps like this, right? It jumps over. It's not so, of course, but that's what the joke. Okay, so the idea is that the displacement current is something which occurs due to the charges that are kind of breathing with respect to the due to the changes of other charges next to them, and therefore they kind of locally transmitting this. You know, if the positive charge is getting closer, then it's pushing away from itself the positive charge on this side, right? It's closing here, and then if they're breathing here, they will also be breathing here. But if they're not breathing, if they're stable, if they're constant, then of course nothing will pass through. So therefore the capacitors do not pass the direct currents, but they do pass the alternating currents. But this is like a side story. So anyway, so the current, this is the main story here. You probably don't recognize it, but this one is something that you all know. It's Ohm's law. Ohm's law. Okay, and it basically says in the integral form that you're all used to, it says that the potential difference or the voltage is equal to resistance times the current, right? But here, if you differentiate this, if you consider it in a small space, in a small piece of space, then if you take the ddx, for instance, right, and then you of course take the ddx of this guy, ddx of the current, then this turns out to be the how you call it, the field line itself, the strength of the field, right? That we will talk about it later, but the strength of the field, and this guy is R times, you know, the density of Y with respect to this one direction. Sorry, that's a horrible thing. Let me maybe draw it a little better for you. So if you take U is equal R times I, okay, then if you assume that you're in a one-dimensional world, then you take ddx of U, okay, then you assume that R is constant, it doesn't change over the ln x, right? And then you take dx of Y, right? The current may be changing with x, right? Then this one is in fact E. This one is we call instead of resistance, we use conductance, okay, which is reciprocal to the resistance, and this is the current density J, okay, and therefore you have J equal sigma times E, okay. So this is basically the current density is equal to the amount of conductive properties of the material multiplied by the strength of the electric field, right? If there is electric field pointed in this direction, right, that means that if you take a particle here and if you let it go, then the field will move this particle in this direction, right? And on the contrary, if you have a particle on this side and if you want to move it, you have to make work against this field, right? And this work in the macro scale will be described by this potential, by this voltage. But in a micro scale, you're talking about the vector lines E, which is the strength of the field, or линия напряженности поля in Russian. And this is the differential equation, which is differential form of the Ohm's law. Okay, that will be important because when we talk about the secondary currents, you'll need this. Okay. All right. So then there is a good news. The good news is that the field in the brain, I had it in the, you can read it in the Sarva's book, and you can read it in Mati Hamalainen in the MEG Bible, the paper like 1989 or something. I think we will have it in all the material, reading materials. But anyway, they show why the quasi-static approximation of these Maxwell equations, in case when we are dealing with the head and with the signals from the brain, is actually working. But the quasi-static approximation means a very simple thing. It just says that the derivatives are very little, are negligible compared. The contribution of the derivatives is very small as compared to the contribution of the actual current. Okay. Therefore, you basically cancel all terms which are talking about the changes in time, right? And then you basically the terms that say that the change in time of something gives rise to something, right? So in this case, the change of time on B gives rise to E, and change of E in time gives rise to B, right? Therefore, the quasi-static field is not propagating like to the outer space, right? It actually dies off very fast. It actually dies off as a square or the cube of the distance. That's the reason why this magnetic field is so hard to catch, right? That's the reason why we spent 45 millions for this magnetically shielded room to isolate the signals that we measure outside from the magnetic field here, right, in the world, in the outer world. Anyway, so the quasi-static approximation reads like this. So you just remove this guy, you remove this guy, and it's 0 and 0, 0. Okay, so now if you can look at this workflow, it's basically all starts with, again, Masha, last time we were talking to you about these dendrites, right, where you have this currents floating, and that will be our primary current, right? This is so-called impressed current, the current that we have created, by, we imposed onto our medium map, we imposed this current, right? And this here is denoted by this white vector here, right? So this primary current, it's of course what the current is. The current is the movement of charges divided by the time interval, right? So it's a movement of it's a derivative. It's the rate at which the charge is changing, right? That's the current, right? So then this displacement of charges creates some set of different charges, and then they give rise to the electric field according to this Maxwell equation, right? So the divergence of E is equivalent to to the density of charges. If it's changed, or if it's simply there before it was not there, then at the place where the charges appeared, non-zero charge density is, then we get electric fields. Electric field itself is creating the electrical, the electrical interaction of charges, right? And the charges start to move along these electrical field lines, right? And depending on the conductivity, depending on the amount of these freely moving charged particles, you'll get the current. If the amount of them is high, you get large current. If the amount is low, you get low. But this current is so-called secondary current. Okay, these are secondary currents here with dashed lines, right, which occur in the entire volume, and the intensity is shown is color coded here, basically. And it's basically, you can see that amperes per meter squared, so it's current density, basically, right? So, and then these currents floating, both this guy, the primary current, and these secondary currents, they give rise to the magnetic field that we are measuring with MEG, and these potential differences that are associated with the presence of E is something that we measure out the currents, volumetric currents that are making outside the skull. They are creating the potential difference, right? And then this way, right? Because these currents also display change the charges, and then the additional electrical field is created. And then this electrical field creates the difference of potentials on the skull or on the scalp that we measure with EEG. Okay, so our goal, by observing this guy B, find where the JP is located. This is a whole task of MEG based neuroimaging, or by observing the vector the potential on the skull, which is very closely related to this E, as you will see now, to find again the source J. The main problem is that this potential on the scalp, it's created not only it's created by the secondary currents that are due to this primary current, right? And the same is B, as the field that we measure outside, it's not only due to this primary current, but it's also due to these volumetric currents. And we actually don't really know very well how these volumetric currents are floating. Therefore, it would be possible, or like next to impossible, very difficult at least, to localize the source. Like it is difficult based on EEG measurements, but in MEG it's a little bit more accurate, because it turns out that for spherical heads, like for Jack in the Box, or like our heads are almost spherical, right? Well, kind of. So you can prove, and we will show. I'll show you today. Just show that the magnetic field outside, the radial component of this magnetic field, does not depend on the secondary currents if your volume conductor is spherical. Okay, well, if you approximate your head by the spherical volume conductor, then you can say that the radial field primarily, radial component of the field primarily depends only on the primary current. Okay, so okay, so now we will be talking about we sometimes will be using current or current density, or sometimes we'll be talking about the current dipole. Okay, so the current dipole is the quantity that is created by the current floating along some distance d, right? And so the longer it is, the stronger the current dipole is. The stronger the current dipole is. Okay, and this current dipole is something that we approximate some small volume where these primary currents are floating and creating certain potential difference. Okay, so, and again, these secondary currents, the total current is equal to the primary current plus volumetric currents. Okay, because volumetric currents are floating here as well, right? Very close to it, right? And so you can, and volumetric currents themselves are so-called ohmic currents from ohm. Ohmic currents, which depends on the local conductivity and the strength of the electric field. Okay, so one little thing, and I think we will maybe we will skip some of this, but because I want to go to the forward operator before the time is up. Okay, so one very, very important property of the electrical field is that, as in the quasi-static approximation, it's so-called curl-free, right? The curl is zero, right? Because it used to be equal dB dt, but because dB dt is too small, then we use quasi-static approximation, and the field is curl-free. Well, if the field is curl-free, then this field can be described, again, the very beginning of the lecture. It can be described by a gradient of some function v. And this function v is nothing else but the electrical potential. Okay, so because you can think that you all know from school, right, that you have a potential, you have in order to compute the potential difference, you have to multiply the field lines, the field strengths, by the distance, right? But if you are in a differential calculus, you have all the d-axis instead of just normal lengths, right? And that's in terms of dimensions, it's exactly this. So this is volts divided by meters, and this is the dimension of this is the units in which you measure E. Okay, but you already know the field, which is very similar to this one, and this is our Earth's gravitational field. Okay, so you have the Earth's gravitational lines, like I've tried to draw them this way, and you all know potential energy. The potential energy is the amount of energy that the body gains if you leave the body with respect to Earth's surface by some height h, right? And so this is your potential energy. From school, you know this expression, and this happens because there is this U is basically a potential of your gravitational field. Okay, and taking the derivative of it, but you can go not the derivative, but just divide by h, right? Divide by the distance. You get mg, which is the force, which is the gravity force that is acting on this body, right? The same here. We are talking about not gravitation, but we are talking about the force that the field with which the field acts on the electrical charges. Okay, the amount of this force, the force itself, is equal to the derivative of the potential with respect to the distance. Okay, here if you assume that u is a function of h, you take the derivative of u with respect to h, you get mg. Mg is your force. You all know, right? The F is equal mg, right? F gravity is equal mg, right? So that's all. So and then very simply, then you basically you can then replace your E in this full current equation. You can replace it with something you can actually measure with V, of course, differential operator of this nabla V, which is simply a gradient of V, right? And with minus sign. Minus is just a convention, okay, so that everything works properly. Okay, and then it's scaled by sigma, right? And then very simply, look, I just want to arrive to the Laplace equation, and that's it, because this is an important piece of evidence, and then we'll go into something simpler. Okay, so that if you take this equation, right, and now if the rotor of the electrical field is 0, okay, then you can if the rotor of the electrical field is 0, then the rotor of the divergence of the rotor, the divergence applied to this E, the divergence of this guy will be let me see. Let me show you this way. Okay, so basically, you can the divergence of J in this case of the vector J, right, will be 0 because the field is basically because this guy is a rotor, and the rotor is something which is rotating and stays within the same volume, so it's not divergent. So divergence of J is equal 0, and then in that equation, if you put the divergence of this guy and set it to 0, then you will arrive to the equation that the divergence of sigma nabla V is equal to divergence of JP, and then the nabla squared V is equal to this. Okay, so that's a very famous equation. In fact, this is called the Laplace equation, and it means that at the point in space where there are no primary currents, the Laplacian, or the second derivative of your potential, of your scalar potential, of your basically electrical potential, is equal to 0. Okay, and your scalar potential is here, and you will basically I think you will definitely, of course, need to read about it between the lectures so that you kind of understand this more. But I wanted just to show you what this means. Okay, so every differential operator can be considered in a finite grid, right? If you want to approximate it with some when you calculate when solve the equations on the computer, then you of course consider these equations on some grid of values, right? You know, then you take XY plane here and split it into little intervals here and put the points, and that will be your grid, right? And of course the derivatives can be approximated, you know, by the definition of the derivative. It's just increase of the change of the function along x direction, for instance, minus the function at the node point, the central point, divided by the amount you moved along x direction, right? And this will be your derivative of u with respect to x, right? And it approximates this derivative quite well, given the h is small, right? And then you can do the same thing about x, and if you substitute the second derivative is the first derivative of the first derivative, right? So then you can take the derivative of this guy and arrive to the approximation of the second derivative. The good thing is that once you done this whole thing and inserted it here, you will arrive to something that will be easy to explain. Okay, you will arrive to this equation. If you require this to be 0, then that means that the value of the potential, let's say this point at the central point, okay, the value potential at this central point is equal to the average value of potentials at this point, at this point, at this point, and at this point. Okay, that means that basically the peak at some location has to be compensated by the value of neighbors. Okay, so it's either everything is 0 or the distribution of the potential follows this kind of profile. Okay, so this is extremely important because this is the Laplace equation which gives you the constraint on the way the electrical potential can change. You can think of splines, for instance, right? If you have spline with limited number of degrees, of freedom, then you can move it only so, right? And then it, if you move this place, it will stick out somewhere else. If you move another location, it may stick out somewhere else. So that's this equation imposes a constraint of how this potential can change. Okay, and this is important. Okay, this is important because based on this, and then setting boundary conditions, saying that, for instance, at some places you have current dipole, and then on the border, like for instance on the border of the, well, let's say the infinity, you should have potential 0, right? And having this and having these constraints, you can set a system of equations and solve for the potential distribution due to a dipole located somewhere in the volume. And that will give you a solution to the forward model. Okay, so I will not delay you, yes, because I'm hurrying, and then it will be no use of this. We will during the next lecture, we will cover a little bit of this. I'll give you some so that you remember at least something. I will go over last 2 or 3 slides again because that's what I rushed very fast and you probably didn't understand anything. So yeah, but we almost done it. Yeah, if I were not delayed by so much, we could have arrived to this formulation of the observation equation of the EG or MEG, so that we are now abstractly working with this matrix G, which is your forward matrix, which is computed based on the Maxwell equations. Okay, and then I will describe to you the anatomy of this matrix, and then we start looking into the inverse model. And yeah, and with Dasha during the seminar, I think you can she will maybe give you some theoretical intro, and you will start already modeling, start to model the brain signals. Okay, so the signal that you measure with MEG based on the activity of sensors given some matrix G, or maybe you will go through the steps of calculating G in M&A Python and show which kind of quantities you need to calculate this, so you understand that the mechanics of it. Okay, the math behind it I kind of described to you, but I didn't, of course, describe to you the way we integrate these equations and the way we arrive to the formula about the magnetic field due to the current dipole. But that's the next lecture. Yeah. Okay. I'm sorry. Yeah. So any questions?
A lot of questions, but
you can
talking
ask
about
now.
myself.
Yeah, but you can. Okay, there is a Google Doc that Dasha has created. Please, well, you can now ask your question, but those who don't want to ask questions now, please do write questions there. Okay, I will take a look at this doc and I will answer them. Okay, I haven't yet. If you've written something, I didn't look at it yet. I haven't looked at it yet. But if you write, I will answer them. Okay. So, but you can ask me the question. Yes, please go ahead.
I mean, I have to, talking about myself, I have to rewatch this lecture to have concrete questions. Now my question is just about this whole thing. What is this?
Okay. Okay. Yeah, that was a complicated lecture. Yes, it was a complicated lecture, but that's something that you needed to have like a big picture. Okay, but the good thing is that you are not going to be like using this in your classes, on your exercises or something, because you will be as I said, you will be abstracted by this matrix G. It will be basically linear algebra and statistics. Okay, but you need to understand how it's all connected. Okay, how it's all connected to basic physics. Therefore, I decided to include this. So it's kind of, I also, for me, also give this lecture is kind of difficult because I have to every time remember it, because I am as well as you. I'm not using this every time, or I've calculated it. I've created some software that computes all these, okay, and which solved these equations on the grid, in the volumetric grid. But it was like a long time ago. But since then I you know, I run it and I
Mm.
compute something and that's it. I'm not changing it, you know. Therefore, so it's okay that you didn't
Okay.
understand, you know, you found it difficult to understand. You need to go
Mm.
through some understanding. You probably will generate with Dasha some questions to you so you can gauge yourself, you can gauge your understanding, you know, the extent to which you have to understand, okay? And then you go over the lecture again and read this Ilmoni Emisarva's book. That also, I need to say that there's a lot more equations, but still it's not quite clear. I mean, but you just have to read it several times, make a big picture, okay? So
Yes, just need to revise and
yes,
rewatch.
yes,
Thank you.
yes, yeah, okay. Thank you for staying with me. Yeah, okay, and for bearing with my relatively fast pace. But next lectures will be slower and simpler. Okay. All right.
Okay, thank you.
Okay, thank you.
Yeah. Okay. Thank you. Yeah.
Thank you so much.
See you
Yeah.
next
Thank
time.
you. Goodbye.
Bye.
Thank you. Bye.
Bye.